Have you ever heard a number so absurd that your brain simply refuses to hold it? What if a machine smaller than your hand just did something that should have taken longer than the life of the universe times more universes than you could ever imagine? And here's the part that makes this story feel almost dangerous. The people behind it are not just claiming a faster computer. They are hinting at a deeper reality that could change how we understand existence itself. Before we go deeper, do this with me right now. Tap, like if you love mind-blowing science. Subscribe if you want stories that make you see the future differently, and share this with one person who always asks the biggest questions. A few years ago, if someone had told you that a tiny chip inside a freezing lab could make the world stop and stare, most people would have laughed. We are used to hearing giant promises in tech. Every few months, there is another breakthrough, another headline, another claim that changes everything. Most of the time, the truth is smaller than the hype. Impressive, maybe. Revolutionary, not always. But this story feels different, because this time, the number attached to the claim is so huge, so strange, and so difficult to even picture that it almost breaks the normal language we use to talk about progress. Google revealed a quantum processor called Willow, and according to the result that sent shockwaves through the tech world, Willow completed a certain benchmark in under 5 minutes. A task like that, if you handed it to one of the fastest classical supercomputers on Earth, would not just take a long time. It would take around 10 septillion years. That is not 10 million, not 10 billion, not 10 trillion, 10 septillion. A 1 followed by 25 zeros. At that scale, the human mind stops feeling the difference. Once numbers get big enough, they all start sounding like the same blur. But this one matters because it tells us something important. We are not talking about a small speed boost. We are not talking about a stronger version of the same machine. We are talking about a gap so large that it starts to look like 2 different worlds of computation. That is why people reacted the way they did. Not because everyone suddenly understood quantum physics, but because everyone instantly understood that 5 minutes versus 10 septillion years is not normal. It sounds like science fiction. It sounds exaggerated. It sounds like the kind of claim you expect people to walk back a week later. And yet, the result was serious enough to be published and discussed at the highest levels of science. So what actually happened? To understand why this announcement hit so hard, we need to slow down and separate 3 different things that often get mixed together. First, there's the benchmark itself, the task Willow performed. Second, there's the engineering achievement, which may be even more important than the headline. Third, there's the wild interpretation that made people start whispering about parallel universes. Those are not the same thing, and if we mix them up, we miss the real story. Let's start with the benchmark. Quantum companies often test their machines using problems designed to show what quantum hardware can do far better than ordinary computers. Critics sometimes hate this, because the task is not always something useful in everyday life. It is more like proving a race car can outrun a truck on a track built for speed. That does not mean the result is fake. It means the test is designed to expose a difference in capability. In this case, Willow ran a benchmark that classical machines struggle with badly. That matters, because quantum computing is not trying to be a slightly faster laptop. It is trying to use the strange rules of quantum mechanics to process information in a completely different way. A normal computer uses bits. Each bit is either a 0 or a 1. A quantum computer uses qubits. And a qubit does not behave like an ordinary switch. Before you measure it, it can exist in a blend of possibilities. Not just 0, not just 1. Something richer, stranger, and harder to picture. That weirdness is called superposition. Then comes entanglement, where qubits become linked in ways that defy everyday intuition. Change the system, and the relationships between those qubits matter in a deep way. When enough qubits work together, the number of possible states the machine can represent grows explosively. This is the part that bends the mind. As the qubit count rises, you're no longer dealing with a system that scales in a neat, comfortable line. You are dealing with something that expands into an enormous space of possibilities. That is why quantum computing excites researchers so much. In principle, this kind of machine can explore structures of information that classical systems struggle to model directly. And Willow reportedly operates with over 100 qubits. Now pause there. 100 sounds small. Your phone contains billions of transistors. Modern chips contain mind-bending complexity. So why does a machine with just over 100 qubits sound so powerful? Because qubits are not competing on the same terms as transistors. This is not a story about quantity alone. It is a story about the kind of information a machine can hold and manipulate. Think of a classical computer, like a person moving through a maze 1 route at a time, even if they move incredibly fast. Think of a quantum computer as something that can set up waves of possibility inside the maze itself, allowing paths to reinforce or cancel one another until the most useful route becomes more likely to appear. That does not mean a quantum computer magically tries every answer at once in the simple way people often describe it. That idea is catchy but sloppy. The truth is more subtle. Quantum algorithms work by shaping probability. They create patterns of interference so that wrong answers fade and right answers stand out. That is where the power comes from. Not from magic, not from a tiny portal in a chip, from the fact that nature, at its deepest level, does not behave the way our common sense expects. And now we get to the emotional center of this story. Because the scary part is not only that Willow was fast. The scary part is that it was fast in a way that makes people ask a disturbing question. Where is the work actually happening? If a quantum machine is handling a structure of possibilities so vast that a classical machine cannot keep up, even in a time span beyond imagination, what physical picture are we supposed to use? In ordinary computers, the answer feels grounded. Electrons move through circuits, transistors flip, operations happen in hardware you can point at. In quantum computing, the hardware is real too. It sits in a lab. It must be cooled to extreme temperatures. Engineers spend years fighting noise, vibration, heat, and error. Nothing about that part is mystical. But when the machine works, it works by exploiting rules that seem to sit at the edge of what reality even means. That is why some physicists, and some very bold voices in the field, connect quantum computing to one of the most controversial ideas in modern science, the many worlds interpretation. This interpretation says that quantum events may not collapse into a single outcome in the way people traditionally imagine. Instead, every possible outcome may continue in its own branch of reality. In simple terms, reality may not be one line. It may be a constantly branching structure. If that sounds like a movie plot, good. That is how weird it is. But it did not come from movies. It came from real efforts to explain what quantum mechanics is telling us. And here is where the story exploded. One of the prominent figures behind Google's quantum effort did not shy away from that interpretation. He leaned toward it. The message was not, "This chip is interesting." The message was closer to, "This result is so hard to picture in ordinary terms that the multiverse starts sounding less crazy." That single idea traveled across the internet like wildfire. Because once you tell people that a chip might be borrowing power from parallel realities, you are no longer in normal technology news territory. You are in the territory of existential shock. You are touching the oldest human questions. What is real? What kind of universe do we live in? Are we alone in this version of reality? Is reality even singular at all? And yet we need to be careful here. Very careful. Because this is exactly where great science can get mixed with great storytelling, and the difference matters. Willow did not prove the multiverse. It did not open a door to another universe. It did not receive messages from alternate timelines. No credible scientist is saying people will step between worlds because of this chip. What they are saying at most is that some interpretations of quantum theory may feel more vivid when a machine like this behaves in ways that stretch common sense. That is a big difference. A breathtaking difference, but still a difference. And many physicists push back hard on the leap from quantum computers are extraordinary to parallel universes are now basically confirmed. They argue that standard quantum mechanics already explains the result without needing that dramatic picture. The math works. The device behaves in ways the theory predicts. We do not need to add another universe to explain every strange success. That criticism matters. Because if we are honest, part of the reason this story became so huge is that it sits at the intersection of real science and irresistible language. And irresistible language spreads faster than careful nuance. Still, even if you reject every multiverse interpretation, something incredible remains. This machine is exploiting quantum interference in a controlled way. That alone is astonishing. It means engineers are no longer just staring at equations in textbooks. They are learning to shape some of the strangest behavior in nature into working hardware. And that brings us to the part of the story that may matter far more than the headline about 5 minutes. Errors. If you really want to know why experts got excited, this is the core. Quantum computers are fragile, painfully fragile. A normal computer can tolerate a huge amount of ordinary life. Heat, motion, electrical mess, all of it. Quantum systems are not so forgiving. Tiny disturbances can wreck the state of a qubit. Information can decay. Coherence can vanish. Noise can overwhelm the calculation before it finishes. This has been the nightmare hanging over quantum computing for decades. Because it is one thing to build a small machine that behaves quantum mechanically for a moment. It is another thing to scale that machine into something useful. The larger you build, the more chances there are for failure. Imagine trying to stack glass sculptures in the middle of a storm. Every new layer increases the risk that the whole thing collapses. That is what makes error correction so important. In classical computing, error correction is already essential, but it is familiar. In quantum computing, it is brutal. You cannot simply copy a qubit the way you copy an ordinary bit. Quantum information has weird rules. Protecting it requires clever encoding across many physical qubits, so they behave like a more stable logical qubit. That has been one of the central dreams of the field. Not just more qubits, better qubits, not just scale, stability. And this is where Willow delivered something many researchers saw as historic. As the system was scaled in the right error-correcting structure, the overall performance improved in the direction the field had hoped for. Instead of getting worse in the expected way, the encoded system showed signs that error correction was actually helping. That sounds technical, because it is. But emotionally, it means this: the latter may be real. For years, one of the deepest fears in quantum computing was that we might be building beautiful prototypes that could never become truly reliable machines. Wonderful lab experiments, terrible practical tools. Willow gave people a reason to believe that the path upward may actually exist. And if that is true, then the implications reach far beyond benchmarks. If fully fault-tolerant quantum computers become possible, they could transform chemistry by simulating molecules that are too hard for classical systems to model precisely. That could change drug discovery. It could change fertilizer design. It could change batteries, new materials, catalysts, and industrial processes. It could help with optimization problems that cripple today's best methods. It could even reshape parts of artificial intelligence, depending on what kinds of algorithms prove useful on future machines. Now imagine that moment clearly. Not a flashy headline, not a viral post. A future where the machines we build can model nature more deeply than ever before, because they are themselves built from nature's strangest rules. That is when this stops being a curiosity and becomes infrastructure. If you're still with me, hit that like button like you just saw the future blink. Subscribe so you don't miss the next shockwave, and send this video to the friend who thinks science stopped being exciting. But before we race too far into the future, we need a reality check, because this field is full of overstatement, and if we are not careful, we end up turning real progress into fantasy. Willow's benchmark was real, but benchmarks are not the same as useful products. Its error correction progress was exciting, but exciting is not the same as complete. And the multiverse interpretation is fascinating, but fascinating is not the same as proven. Those distinctions are everything. This is where a lot of public conversation goes wrong. People hear one giant number and assume the entire future arrived overnight. They imagine passwords instantly broken, every scientific problem solved, every laptop replaced. That is not where we are. The most serious experts still talk about the road ahead as hard, expensive, and uncertain. Building useful, fault-tolerant quantum systems requires far more than a stunning demonstration. It requires logical qubits that live long enough, gates accurate enough, architectures scalable enough, and software clever enough to turn raw quantum behavior into real outcomes. Every one of those steps is brutal, and the competition is growing. Google is not alone. IBM has pushed its own quantum roadmap. Ion trap systems, photonic approaches, superconducting platforms, neutral atom systems, and other methods are all competing to become the foundation of practical quantum machines. Different teams believe different physical approaches may scale better. Some prioritize coherence, some prioritize connectivity, some prioritize manufacturability. The race is wide open. That matters, because history teaches us something important about breakthrough technologies. The first company to shock the world is not always the one that dominates the final era. Being early matters. Being scalable matters more. So where does that leave us right now? In a strange place, a place between proof and promise, a place where the machines are already real enough to force serious people to rethink what is possible, but not yet mature enough to deliver the full practical revolution they hint at. That in-between moment is often the most fascinating phase of any technology. It is where you can still feel uncertainty. It is where belief and doubt coexist. It is where the future is close enough to touch, but not close enough to own. And honestly, that may be why this story hit so deeply, because Willow is not just about computing. It is about human perception. We like reality to feel stable. We like our tools to obey intuition. We like progress to come in neat steps we can measure and compare. Quantum computing refuses to do that. It shows up wearing the language of engineering, but carrying the soul of philosophy. You think you're watching a hardware story, then suddenly you are arguing about the structure of existence. That is rare. Very rare. Most technologies extend the world you already understand. Quantum computing threatens to expose how little we ever understood it in the first place. Maybe that is why people cannot look away. Because beneath all the technical terms, beneath the cryogenic systems and error rates and benchmark design, there is a simple emotional truth hiding in plain sight. We built a machine using the deepest weirdness we have ever discovered. And now that machine is starting to answer back. Not in words, not with a voice, but with results that force us to take the weirdness seriously. Think about the history of science for a moment. The telescope did not just improve vision, it destroyed a comfortable illusion about our place in the cosmos. The microscope did not just magnify water, it revealed hidden worlds alive beneath our notice. Particle physics did not just split atoms, it shattered the idea that matter was simple and solid in the way it appears. Again and again, our tools have humbled us. Again and again, every time we thought the world was basically understandable, a better instrument arrived and showed us that reality was stranger than our instincts. Quantum computers may be the next instrument in that tradition, not because they are merely faster, but because they are built from a part of physics that still feels unfinished in the human imagination. And the moment those machines start doing things that classical systems cannot realistically track, the old philosophical questions return with force. What is computation, really? What is information? What does it mean for possibilities to interfere with one another? Why does the universe allow this at all? These are not childish questions. They are profound ones. And they matter because civilization may soon depend on technologies built from answers we still do not fully understand at a conceptual level. That has happened before. People used fire long before they knew chemistry. People used electricity long before they understood quantum electrodynamics. Engineers often learn to control forces before philosophers and theorists finish agreeing on what those forces mean. Quantum computing may follow the same pattern. We may end up using machines powered by principles that still feel metaphysically shocking. If that makes you uncomfortable, good. It should. Discomfort is often the emotional price of real discovery. The universe does not owe us familiarity, and the more powerful our tools become, the more likely they are to reveal truths that do not fit the human scale we evolved for. A predator in the grass, a storm in the distance, a face in the crowd. Those are the scales our brains were built to handle. Not qubits dancing in superposition, not probability amplitudes interfering, not branching interpretations of reality. So when a company says a chip solves something in 5 minutes that a supercomputer would need 10 septillion years to finish, the shock you feel is not only about speed, it is about scale. It is about mismatch. It is about the terrifying possibility that the universe has computational room we barely knew existed. And once you feel that, even for a second, ordinary headlines start to seem small. Because now the question is bigger than Google, bigger than one chip, bigger than one industry. The question is whether we are standing at the edge of a new scientific age where our machines do not just help us calculate faster, but force us to rewrite the story we tell ourselves about what reality is. That is why some people are cautious. And that is why some people are electrified. Both reactions make sense. Caution protects science from turning into mythology. Excitement protects science from becoming emotionally invisible. We need both. We need the skeptics who insist on careful language. We need the dreamers who dare to follow the implications. Without the skeptics, we fall for headlines. Without the dreamers, we miss history while it is happening. And right now, history may be happening. Not finished, not settled, but happening. We may look back on this era as the stage where quantum computing stopped being a scientific curiosity and started becoming a genuine technological path. Or we may look back and say this was one dramatic step in a longer journey that still had many walls ahead. Either way, it matters, because once a field crosses from interesting in theory to demonstrably doing something extraordinary in hardware, the world changes its posture. Investors pay attention. Governments pay attention. Researchers flood in. Rivals accelerate. The timeline compresses. What felt distant starts to feel urgent. That is how technology races begin. And if you want one more reason the Willow story matters, it is this. It forced millions of ordinary people to look directly at quantum mechanics again. Usually, quantum theory lives in classrooms, papers, and documentaries. People hear that it is weird, nod politely, and move on. But when that weirdness suddenly appears inside a machine that may shape medicine, energy, security, economics, and AI, it stops being abstract. Now it is personal. Now it is political. Now it is strategic. Now it is about power. And power changes everything. The nations and companies that learn to harness these systems first could gain enormous advantages in science, defense, logistics, materials, and cryptography. That does not mean tomorrow morning, but it does mean the race has consequences. This is no longer just a niche experiment. It is a frontier. And frontiers have a way of attracting ambition, fear, brilliance, and hype all at once. So if this story feels bigger than a normal chip announcement, that is because it is. It is a collision between engineering and mystery, between measurable performance and philosophical shock, between the clean language of hardware and the messy language of reality itself. Drop a comment with the one word that describes your reaction. Subscribe if you want more stories that hit harder than fiction, and share this with someone who still thinks the future arrives slowly. Now let's come to the most important question of all. What should we believe? Here is the honest answer. Believe the achievement is real. Believe the engineering progress is meaningful. Believe the benchmark was designed to show quantum strength, not everyday usefulness. Believe the error correction milestone may be one of the most important parts of the whole story. Believe the multiverse interpretation is a bold and controversial way of thinking about the result, not a proven fact. And believe that even the cautious version of the story is still astonishing. Because it is. You do not need parallel universes to be amazed. You only need to accept one thing. Humanity is learning to build machines out of rules we barely learned to describe a century ago. That alone is incredible. And the deeper truth may be even more powerful. Sometimes the biggest technological leaps do not just give us new tools, they change the emotional atmosphere of the world. They make the future feel heavier, closer, less theoretical. That is what quantum computing is starting to do. It is moving from concept to consequence, from math to machines, from curiosity to pressure, from someday to watch this space very carefully. And once that shift happens, there is no going back, because every new milestone will now be measured against a different question. Not, is quantum computing interesting? That phase is over. The new question is, how fast is this becoming real, and what happens when it does? That is the question governments are asking. That is the question industry is asking. That is the question cryptographers are asking. That is the question every serious lab in the field is asking. And maybe, after Willow, it is the question the rest of us should start asking too. Because if the road continues, if error correction keeps improving, if logical qubits become stable, if useful algorithms mature, then the machines coming after Willow may not merely impress us. They may reorganize parts of science and industry from the ground up. New molecules, new materials, new drugs, new strategic power, new risks, new forms of inequality between those who can access the technology and those who cannot. Every major revolution carries both promise and pressure. Quantum will be no different. That is why this moment deserves more than hype. It deserves attention, careful attention, the kind that looks past clickbait and asks what was actually demonstrated, what still remains uncertain, and what signals a real turning point. Because if you can learn to separate spectacle from substance, this story becomes even more impressive. You begin to see that the real wonder is not in one dramatic phrase about stopping the world. The real wonder is that after decades of theory, failure, patience, doubt, and engineering pain, a machine built from quantum rules is starting to deliver results so striking that even the cautious people in the room are no longer comfortable dismissing the future. And that may be the most powerful part of all. Not that the world stopped, but that the world paused, looked, and realized something important. The age of quantum computing is no longer a distant rumor. It is approaching with enough force that even now, before the full revolution arrives, we can already feel the ground shifting under the story of what computers are. So the next time you hear someone say this is just another tech headline, remember what is really on the table. A machine colder than deep space, a result beyond normal intuition, a field racing toward stability, a debate touching the foundations of reality, and a future that may judge this moment as one of the early signals that a new chapter had begun. Maybe the wildest claim will fade. Maybe the multiverse language will prove too dramatic. Maybe better explanations inside standard physics will satisfy everyone in the end. But even then, the core fact remains. We are building devices that force us to take quantum reality seriously, not as an abstract theory, but as a working resource. That is not small. That is not ordinary. That is civilization level strange. And if Willow is even a glimpse of what comes next, then the most shocking part of this story may not be what happened 5 minutes ago. It may be what happens in the next 5 years.